first. All right. Does anyone have questions from homework or the quiz or the fact that we have another quiz this Wednesday? What? Evil person. Yes. I'm evil. All right, guys, let's have a little discussion. I really hope that I have not somehow come off as a person you cannot ask questions of. I really hope that I'm not subconsciously doing something. Am I coming off as a mean person? I don't know. I live off of questions. And when you guys go into groups, do you not realize how many other people are also confused? So you should not feel held back about asking questions because you think you're the only one with questions. You know that's not true. No. There's, we have so this chapter 4 quiz is right on the heels of us doing chapter 4 homework. It's if you do the homework, you'll be fine on the quiz. I will have a practice midterm since we have a midterm coming up. And don't forget the midterm is going to be in class, on camera. Everybody's camera will be on when we take that bad boy. All right. I do have a worksheet today that we're going to start off with. If there's no questions from homework, that goes over section 4.3. Hello? Yes?
I have a question on number 32.
All right, let's see. I'm so excited. There's a question. Let me see. Hold on. 32. Oh, yeah. All right. On average, how many years would you expect a child? So they give you a couple of clues there on average and expect. So expected value. What's the formula for the expected value?
Is it sum of x times probability of x?
Yeah. So for number 32, what you need to do is and actually they have it here. So yeah, so I forgot which one I was doing. So there's another problem earlier that's got the same kind of question. And you do the exact same thing. So this one is just to do 32, you sum up this column. Right, so the formula for the average, which is also known as the expected value, that formula is sum of xp of x. Is that cool? So you just have to first create all of these in that column that was up there, and then you have to add them.
Okay.
Cool. That's all you got to do.
I had a question on number 70, the one with the Broadway tickets. I know there's a couple on the homework that are similar.
Yeah, like 36 is actually similar, but let's take a look at 70. Let's see. I was just taking a look at 70 just a minute ago.
Sorry.
Oh, sorry. That's right. I think it was during office hours. So what you want to do, in fact, they pretty much tell you. So hopefully these first few, A might be a little weird, but obviously you're interested in winning, you're interested in the money, whatever. B is, all right. The reason they ask part A is so that you make sure to know what the variable stands for. So what are you interested in here? I basically just gave it away. It's the money. So then the variable should be the values of money associated with the outcomes. What are the possible outcomes in this scenario? I buy some tickets. What could happen?
They're $5 a piece.
Sure, they're $5 a piece, but once I buy them, what could happen?
Your value goes down of the Broadway show?
No. Let's
I'm
no.
confused.
So why am I buying the tickets? It's a raffle thing, right? So what could happen? I could buy a ticket that does what? Or I could have no tickets that do what? What?
Oh, that you win the raffle.
Win. All right. So what could happen? I could win or
Don't win.
sweet.
Lose.
So let's figure out first. I buy 4 tickets. How much money am I already out?
$20.
So I'm out $20 already. So if I don't win, if I lose, what's my money situation?
130. Oh wait.
If you win, it's 130 because it's 150 minus the 20 it took just to buy tickets. That's 130 profit. If I lose,
$20.
I'm out 20. So make sure it's negative because
Okay.
that's flowing away from you. So it's got to be negative. Positive means flowing towards me, right? So for any casino game, the expectation is negative, flowing away from you, right? Okay. All right. Now you got to figure out the probability of these things happening. What's the probability that any single ticket wins?
1.
1 is 100%. What do you mean? 1 out of
100.
Okay, thank you. So what's the probability we win? We bought 4 tickets. So what's the probability we win?
4 out of 100.
Yeah, 4 out of 100. So what's the probability we lose?
96 out of 100. Womp womp.
I appreciate you trying with everything happening in the background. I like it. Is everybody with this so far? Do you guys see this? It's can you articulate the outcomes in English? Then what are the numbers associated with the outcomes? Then what are the probabilities associated with the outcomes? And then I can do x times p of x. And then I can add them up, and that would be my expected average winnings. So if it comes out positive, that doesn't mean you're going to win. It means that if you did it a lot, you would come out ahead. If it comes out negative, that means if you played this game a lot, you would come out behind. That's what that means on average, right?
Yeah, thank you.
You're welcome. Okay. So that's how we can make a decision as to what to do. The less of a gambler you are, the more positive, the higher the positive expected value has to be before you'll do it. And the more of a gambler you are, you could even do it if the expected value is negative. You would still do it because you're like a gambler. You're going to take chances because it's on average, right? So one person could win $1 million, but that means that thousands of people lost some money. So overall, it actually averages in favor of the house, right? I don't know if you guys are with me on this. So that's a weird little problem. They use a little bit stilted language, but that's how we calculate an expected amount. We make an XP of X table, and then we do the X times P of X. Then I see on average, how much am I going to make or lose?
Yeah, what threw me off was with the other problems, it's like a bigger.
Oh, yeah.
Yeah, like
It's like a longer table.
Yeah, and then these are just 2.
These are just 2. Exactly. So don't let that throw you off. You go, oh, thank God, there's only 2 things. So be really careful because there could be a problem where there's multiple ways to win. Like you could have a 1 out of 100 chance to win the grand prize, and then a 3 out of 100 chance to win the second place prize. So there might be a problem where there would be more, because it isn't just win lose. It's win this or win this or win this or lose. Right? Does that make sense? You could have multiple levels of prizes. This one was really nice, but like you said, it's also evil because you expect more, and it's really just bam, bam, 2 things. There's only 2 things that could happen. People mix up the 100 and the 4. Those just tell you what the probabilities are going to be. They have nothing to do with anything else except the probabilities of the outcomes. All right. Maybe. Real quick. I'm going to erase this. Everybody ready for that? This is all going to go away. You guys cool with that? Okay, here it goes. It is gone. Is anyone about to turn 25 or just turned 25 out of curiosity? Anybody? Nobody? Anyone around that age? Is it? Nobody wants to say anything to me. All right. Yes. Does anyone know what happens at 25 financially? How else do I say this? Car insurance.
It lowers your insurance, doesn't it?
Yes. Why? So what they do, it's a little bit more complicated than this, but it's actually not that much more complicated. Yeah, you can rent a car at 25 because statistically, people who are above 25 get in less accidents. And then people will say, oh, no, I know this guy's 31, he got in an accident. That's not what I just said. Statistically, people above 25 get in less accidents. So they'll make a table, and they'll say, all right, if you're 24, here's the amount of one accident, I don't know how much, $10,000, whatever. And the probability that is going to happen is going to be 30% chance or whatever, and then blah, blah, blah. And then when you hit 25, these probabilities change. Then it becomes more likely that they'll have to pay out nothing for you. So when they calculate your the overall expected value, is everybody semi with me? So this would be the amount of money that they pay out and the percentage of the time they had to pay that amount out for somebody who was 24 or 23 or whatever. When you hit 25, these numbers change drastically just because of the overall average. Just the people who are 25 suddenly they get in less accidents for whatever reason. So when they calculate this overall expectation, it goes lower. They expect to have to pay out less. So they're going to take less money from you to cover for that. Does that make any sense to anybody? Are you guys semi with me? So it is a little more complicated than this, but not really that much more. There's little extra probability considerations based on, where you live, how far away from work do you live? Are you a good student? You get a discount for that, right? For being a good student because you're a better driver, statistically speaking. All right. Woo! So this is, sorry, go ahead.
Could we go, because 75 is something like that where it has, I guess, a lot going on.
Oh yeah, the big thing to realize for 75 is there's 3 separate companies, right? 3 separate investments. So let's just look at one investment and then the other 2 will be the same. So here's the first investment. It's a software company. So I can start collecting my stuff together. So this is for the first investment. So what are the possible outcomes? I could make a $5 million profit. And what's the probability of that? 10%. I could have a $1 million profit. And there's a 30% chance of that happening. Is everybody with me? It's just filling in the blanks. And then a 60% chance of losing $1 million. Oh, shit. And so that should be negative. And now you just do your XP of X and you can figure out your expected value. I like it.
Got it. Thank you.
You're welcome. Has anyone ever seen the movie Along Came Polly with Ben Stiller? It's probably too long ago for most of you guys. Anyway, he was a risk analyst. And a lot of his work he did was based on these kind of tables. Anyway, sorry. That's a very obscure movie reference. I understand. So you just have to do this kind of table 3 times because there's 3 companies and investments. I like it. Is that cool, everybody? You guys all right out there?
So for the last one, since it says a 70% of non-profit or loss, would that be 0?
Yes, you put a 0 in for X. So some people might like that, a high chance of nothing bad or good, right? And obviously, a high chance of good is better, but in the cases of losing large sums of money, you might be okay with coming out breaking even. Okay. Anything else, guys? So when you see them say construct a PDF, that means a probability distribution function. I don't really call it normally a function. It's just a probability distribution, which is what this is. We used to call these frequency distributions before we started calling these probabilities. And so all of a sudden we call them probability distributions. Crazy. All right. Anything else from homework, everybody?
Could you explain how to go through problem 36?
Okay. So that's the one that's like number 70's little brother, but it's a little bit weirder in a sense. Let's go back to it. Come on. Rawr. So you got to remember what kind of sucks about this one, and I think I try to prepare you for this because we talked about face cards, and I specifically did it thinking about this problem. I'm going to put it down in their bottom so I have some room. So you draw a card from a standard deck. So again, can you tell me in English, what are the outcomes of this whole thing, about this game? What could I do?
Get a face card or not?
Well, sure, but if I get a face card, I win.
Win $30?
Good. All right. So if I win, I get $30. So that's positive 30. What happens if I lose?
You pay $2.
Pay $2. That's going to be negative. Now you figure out the probabilities of each of those things. What is the probability of getting a face card? How many face cards?
12,
Good. Out of?
52.
Good. All right. And I'm going to not do any more because now you just got to figure out what goes here for the rest of the probability. Then you do your X times P of X. You add them all up and you see what the expected value is. It's going to come out. Whoever set this game up was kind of dumb. It comes out really big positive, which means hell yeah, you play that damn game, right? You play the game a lot because you might lose a couple times, or you're going to win more often. And when you win big. So overall, you should come out ahead. I really want that understood. If you only play the game once, if you're only going to do this once, this table doesn't mean shit, right? Because either you're going to win 30 or you're going to lose 2. If you play the game 100 times, then the expected value comes out meaning something. So most things about probability only really take on a full meaning over the long run, right? So if I say probably flipping a heads is 50%, that has nothing to do on a single flip. But if I flip it 1,000 times, now I can say I expect 500 heads. Expect X times P of X, right? Or in that case, N times P, but you get the idea. Hopefully. Is that good? Did I go too far with my rambling about shit?
No, it's good. Thank you.
Okay, thank you.
Yeah.
So in this section, it's all about, can you take the situation and turn it into an X P of X thing? Then you can analyze the hell out of it. Okay. All right, guys. Anything else? All right. So let me show you this. Is everybody able to access Canvas right now? All right. So if you go to Canvas, go to our class. If you go down to modules, Whoops. Go down to unit 4. Yeah, unit 4. You'll see binomial practice. So if you could print that out, or you don't have to print it out. You just pull it up, whatever you want to do. Pull it up on the screen, print it out, whatever the hell, right? Let me just, well, let's see. Let's review a little bit right here. We created this formula last time. I took you through to show you why this formula only makes sense. This first piece, well, crappity do that. This first piece deals with how long the list would be. And then these are both, I've got this many successes and this many of the rest are failures, right? So in this case, if I wanted to know, I have 44 San Diegans and there's a 15.2% chance, and I want to know probably I get exactly 3, that would be 44, choose 3. I got 3 successes and 41 of the rest, 41 failures. So these two exponents always have to add to be the total number of people. I'm breaking them up into 2 groups. And then I put a little note about how it looks in the calculator, right? 44, you hit the math button, probability, the third option, blah, 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 blah. But just to remind you guys how to plug that thing in the calculator. So what I want you to do is pretty obvious. I want you to work on this, and then I'm going to break you up into groups. Because normally is when I break you up into groups, like I said earlier, is when I find out how lost people are, because people don't like to tell me for some reason if they're lost in general. So do as much as you can of this on your own, and then I'll throw you guys together in groups. You can complain about how little sense I make or whatever you like to do, maybe even work on the problems. And then we'll do the worksheet together. All right, let's see if anybody complains if I do this. No, okay. So go ahead and start working on that sheet. I'm gonna do, okay. So I didn't make it as far as I thought I did. Let's talk about, hopefully you're at least approaching part D, right? Where I show you 2 formulas. Well, let's see, this will be relatively quick, to be honest. I'm not even gonna get off my ass to do this. So, so to find the mean of a binomial, so I want you to realize what's happening. Remember when we did section 4.1 and 4.2, we had the x and the p of x. And so we thought, okay, I always want to figure out the mean and the standard deviation for any set of data that I'm given. When I'm given data in a different format, like the x p of x thing, I don't want to do what I did when I had a list of data. So we created a new formula. It actually does the same thing the other one did before, but it just looks new. It works with the x and the p of x more directly. With a binomial situation, it is yet again another way to be given data. So I still want to know what the hell the mean is. So tell me this. If the percentage of all San Diegans who smoke is 15.2%, and you pick 44 San Diegans, what's your best guess for how many of them smoke?
15.2%.
Of them, exactly. So your best guess, the expected number of people who smoke would be the percentage of everybody times the 44. Does that make sense? Right? No? So roughly half of anybody is half of anybody. How do I say this? So like, let's say half of people like, how do I say? Half of all people like taking an online class. So if I took 40 people, how many of them would I expect to like an online class? 20. Half of them, because half of everybody does. I really want this to make sense. So what is the formula for the average expected number of people that do whatever? It's N times P. It's the percentage of the total. Does that just, please just let that, this is never a good thing to say when you teach, but please just let that make sense. So it's going to be 44, and I want to take, what was it, 152, 15.2% of them. That's how many I'm going to expect. It's going to come out to be a decimal. So what? Averages can come out to be decimals. We know that. Now, the standard deviation is a lot harder to explain, but this is the formula for the standard deviation. And it's the easiest. Isn't this the best? These are the best. It's a mean. I don't need to make a table. I don't need to add a lot of shit up. I just do N times P. And the standard deviation, it's only got a couple more things, a square root and a cube. Those kick so much ass compared to every other way we've calculated these things so far. Are you guys, either you agree or you don't understand what I'm saying? Because you agree, period. These are the best formulas yet. All right. And you're like, well, Jeff, I never understand what you're saying. Well, shit. All right, so this would just be that, and this would be the square root of 44 times 0.152, 10 times 0.848, whatever the hell that is. Okay. Yes.
Can you go over one of the questions in B?
Why am I doing it like this? Darn it. All right, let me clear this away. Here it goes. What, this guy?
Yeah. I'm just having trouble getting it into my calculator.
What do you mean getting it into your?
When I put everything into my calculator, it's not coming out with an E.
Oh, I'm pretty sure that's the one. Did anyone else get an E on that one? Anyone done that yet?
Yeah, I got the E. I'm just not sure what to do once I'm there.
E is to the, right? To the.
Yeah, it means times 10 to the. So if I get something like 1.7 E negative 4, that means 1.7 times 10 to the negative 4. And all that means is move the decimal back 4 places. 1, 2, 3, 4. So that's what that number would be. I'm not saying that's the answer you get for part B. I'm just telling you in general, that's how to interpret E. It's just scientific notation. So all it really means is move the decimal this many times in this direction. So it's negative, so it means move it that way. If it was positive, it would mean move it that way. It's just a nice way of writing a number without writing all the frickin' zeros, right? Frickin' zeros. All right. So I'm going to go ahead and break you guys up. And you guys talk about all these things. You can get, if you need to complain about whatever, get it out your system. That's great. Now's the time to do it. Here we go. And then I'll get you out of there in a few minutes. Oh, I should stop. Good job, Jeff. So that's 1611. So what does that mean? That means there's a roughly 16% chance that exactly 7 people out of 44 will smoke. Okay. So what's slightly more useful than knowing exactly 7 is knowing what's the probability that none of them smoke. So if I'm in a big room and I'm at 44 people are coming, should we have gotten an ashtray? What's the probability that we're okay since we didn't get an ashtray? That we could figure that out right now. This would be the probability that nobody's going to smoke. So it's going to set up a lot like what we just did. 44 people. I want to choose nobody this time. So I have no successes and they're all failures. So the biggest problem I see is somebody puts a 37 here again, because they put a 37 here last time, but that makes no sense because these two exponents have to add up to be everybody because we have to put everybody somewhere. All right. So this is where, when you, let me show you what you get in the calculator. So there's the formula. Let's go to the calculator. Come here, calculator. Where are you? No, this one. Okay. So now I'm going to do 44. Scheisse. There we go. Choose nobody. Hit the over arrow times 0.152 to the none of them. I'm going to show you a shortcut in here in a minute for this one. Times 0.848 to the all of them. And this is where you get the weird E shit, right? So real quick, I want to ask you guys, what is 0.152 to the 0 power? What is anything to the 0 power?
0.
If it were 0, the answer should have been 0.
Never
So
mind.
it can't be 0.
Isn't it like 1 or something?
It's totally 1. I love it. Real quick. Why does that make sense? Because answer me this. What is x cubed divided by x cubed? Isn't that 1? Well, what's another way you can do it? What do you do when you divide things with powers like this? What's 3 minus 3? 0. Oh, snap. Anything to the 0 power is 1. Done. Yay. All right, what's that got to do with anything, Jeff? Stay with me. This is a really small point, so I'm not going to. How many ways is there to choose nothing from 44? How many ways can you choose nobody from 44 people? One way. I choose no one. You know, there's only one way to do it. Okay, so that's 1. So if I just did 0.848 to the 44, I get the same freaking answer because this is 1 and that's 1. Do you have to know this? No, if you understand what I'm saying here, it's a little bit quicker when you got zeros, but you get the same answer even if you put the whole thing in there. So you're fine. If you don't understand, you're okay. All right, maybe. So let me stop this. Let's go back here. Let's see how the hell do I write this thing down? This weird ass E thing. So it was 7.069. So let me call it 7 times 10 to the negative 4, right? Which will be, move the decimal 1, 2, 3, 4. So it's going to be 1, 2, 3 zeros, 7. Isn't that rounded to 4 places? I can forget this other shit, right? Let me stop for a minute. Is everybody okay? So that's what it means when I get an E. E means times 10 to the. Okay. And then this problem, what I think we talked about it, right? What's the opposite of at least 1 is none. And how do opposite probabilities interact? 1 is 1 minus the other one. Right? If the probability is going to rain today is 10%, what's probably not going to rain? 90%, the rest. So if I want to know the probability that at least one person will smoke out of 44, then I can do 1 minus none of them smoke. I've got that right there. So I get that. So if I got 44 people coming and I have no ashtray, I am probably in trouble, right? Because it's a 99.93% chance that at least one person is going to smoke. Okay, maybe. All right, there was something else I was going to say. What was it? I forget now. Shoot. Oh, well, I can't remember. Is everybody okay with those 3 right there? You guys good? Okay, all right. So now it's just a couple of formulas. Just got to throw stuff in. So I know N is 44. I know P is 0.152. What'd you guys get for that?
6.688.
I get 6.688. So that means approximately 7. I have no idea. Don't ask me why there's so much space between my 8s and my 6s. There. Okay. So if I had to estimate how many people would smoke, I would say about 7. I have 44 people coming, 44 San Diegans. I would expect about 7 on average to smoke. That's the expected value formula if I have a binomial situation. All right, and now what's the standard deviation? It's the square root. 44, 152, 848. So you got to throw all that business in there. What do you guys get for that?
2.381.
Yeah, 2.381. I love it. Round it to the right place and all that kind of shit. I love it. Now, here's the thing. This is something that we can do this kind of thing now. This idea of unusual is finally a really good measure of what the outliers are. Right? So there is one I could use with quartiles and all this kind of bullshit. That's not used as much. This idea of unusual being more than 2 standard deviations away from the mean. Right? Because if I had a normal curve, what percentage would be more than 2 standard deviations away would be 5%. So that would happen 5% of the time. So they would be unusual to see it. If I see somebody whose height is more than 2 standard deviations away from the mean, they're either exceptionally tall, like unusually tall, or unusually short. They're off from the normal. Okay. So if I put the mean right in the middle, 6.688, and I go up 2 of these. So I go up 2 of these, and I go down 2 of these. Where do I end up?
For down will be 1.926, and for going up will be 11.45.
11.45?
Yes, sir.
Okay, thank you. 2.381, Kevin, because it was 2.38147, right? So it's 2.38147, blah, blah, blah. That's a 4, so that stays a 1. Don't do dominoes. Don't make that 7, make that a 5, which makes that a 2. No, 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 no. It's the exact next number. 147 is closer to 100 than it is to 200. Correct? Okay, so that's why you don't make it a 2. So would it be unusual if I had a group of 44 San Diegans and 15 of them smoked?
Yes, because they're outside the 2 standard deviations.
Good. 15 would be way the hell up there. So if I had a random group of 44 people come and 15 of them smoked, I would say, do you guys know each other? What's going on? Are you guys part of a club? Right? Does that make sense? No. So there was I can't remember if we did this before, but I believe at some point I was talking about, well, if you flip, let's do this. Let's do this. If you flip a coin, I have no space on this. Is everybody cool with this worksheet? Any other questions on this before I say what I'm about to say? Everybody's cool with this? Okay. Let's do this and see if anybody else. No. Okay. Now, let me turn off my dinosaur, which is a phrase. I love that we're saying that phrase now, and it makes sense. Everybody turn off your dinosaur. All right, there we go. It's just obscure music day for me. All right. So watch this. I believe at some point during the semester, I said, what if you flipped a coin, let's say 600 times, let's say 500 times. How many heads would you expect? So the question you should easily be able to answer. If I flip a coin 500 times, how many heads would I expect to show up?
250.
250. So I expect about 250. So my question now is, would it be unusual? When does unusual start? Would 240 be unusual? What do you think? If I got 240, would that be unusual or is that okay?
That's okay.
That's okay. Would 210 be unusual? Maybe. Well, let's see what we get. We know how to do this shit now. So where'd 250 come from? It actually came from this. Well, it really didn't come from this, but you guys see how this is the work you did? 500 times 0.5, because there's a 50% chance getting ahead. All right, so that was 250. Now, what's the standard deviation? Square root of NPQ. That's going to be roughly 11. What do you think, Jeff? 11 point, I don't know, 11.07? I don't know, I'm just making the rest of that shit up. That's it. Yeah, that's right, Corbin. Let's see. 11.18. Damn it, Jeff. Let me stop for a minute. This is exactly what we just did, right? So now I have a definition. We have a technical definition of where unusual starts. So if I put in the middle 250 and I go up 2 of these and down 2 of these, that would take me up to 272.36, and it would take me down to, I don't know, 22 to 27.82. Is that right? I don't know. I don't know if that's right. Nobody's going to help me because nobody cares about me. No, nobody can help me. Does anyone know what I'm doing to get that number? Do you guys understand what's happening? I just did 250.
You're right. It would be 272.36, and let me check the other one.
Okay. 250 minus
227.64.
227 point. Oh, Jeff, I was so close. I'm sorry. I'll retire. I'm done. Can't do math anymore. So if I flipped a coin 500 times and I got 212 heads, is that evidence that it's been tampered with? I get 212 heads. Is that evidence that it's been tampered with? Yes, I love it. People confuse evidence with proof. Is that proof it's been tampered with? Hell no. Because even though it's unusual to get 212, is it impossible to get 212? No, it's not impossible to get 0 heads. It's not impossible. But if I got 0 heads, screw it. That thing's been messed with. Holy shit. It's so unlikely that would be strong evidence. This is evidence. This is stronger evidence. This is insane amounts of evidence, right? If I get no heads at all, I'm so far away from what I expected. Screw it. That thing is weird. Okay. All right. Maybe. So we have a technical, formal kind of way to determine what is unusual. So if I, for example, Aaron Brockovich. Do you guys know the name Aaron Brockovich? No.
Yes.
Yes, some of you guys know. So she did the whole thing about PG&E, the gas and electric company of California, poisoning the water supply and killing people basically with high occurrence of cancer. So you could do a study and you could say, I would expect this many cases of cancer, right? I would expect this many cases of cancer. This is the least and most. But in this town, I see this much cancer. That is evidence, not proof, but it is evidence something is going on. It could just be a random blip. But if it's here, then I'm going to go in and start testing the water, test the air. Do you understand? If I find nothing, then I'm like, that's just a random blip. That's not impossible, but it's unlikely. So it just makes me go, let's go. And if I got something down here, then I go, whoa, what are they doing? They seem to be keeping cancer away. Holy shit. Okay. I like it. By the way, have I talked to you? I'm pretty sure I talked to you guys about the vaccine and people that die after taking the vaccine. Have I talked to you guys about that?
Yes.
I did. I thought I did. And, you know, this same kind of thing, you have people and you have an average amount that you expect to die. And so when you give them vaccine, we actually saw this many deaths, a little less than would be expected. And then you have all the anti-vax people going, look, it killed people. And you're like, people gonna die. I'm sorry. If nobody died after taking the vaccine, that would actually be really strong evidence that the vaccine makes you live forever, right? And like, holy shit. So if you hear some idiot trying to say, don't take the vaccine because people died after it, you go, well, people die after checking their mail. People die after eating some macaroni. I mean, people just, I'm sorry, people die. So anyway, sorry, that's enough of that. So hopefully that makes some sense to you. Be careful about misinterpreting situations. Okay. All right. So last thing for today, how much time we got? Not a lot of time, Jeff. Okay. So I'm going to do a little bit. Thanks. That's, yeah. If you take anything away from my class, it's the fact people die. Just deal with it. All right. And again, I not to be callous, if anybody has lost anybody, obviously, but you understand what I'm saying. You understand my point. This happens. It doesn't mean that something caused it to happen. All right. So last thing for today, very quickly. Believe it or not, this has to do with the next section. And I want this to make just tons of sense, as with everything I do. There we go, Jeff. All right. So this is kind of cool. Why is everything so weirdly?
A quick question.
Yes.
So the worksheet that we just did right now, would that be kind of like our study guide for the quiz that is coming
Well,
up?
be careful. That worksheet was just 4.3.
Oh,
okay. So let me just remind you of this. If I remember, I can post the answers we just did if you want to. Then we have this other one. So together, I pretty much gave you a practice quiz, to be honest, because the other one we did was this one. So this goes over 4142, right? There's a worked out example, and then we did this side together. And then the one we did today is 4.3. So together they're 4.1, 4.2, 4.3. They're the whole chapter 4. So those are two excellent worksheets to look over to be ready for that quiz on Wednesday. Okay. And just remember, tell me if you want the study group to meet. I can make the Zoom room thing again. You just got to let me know. All right. So last thing for today. All right. Has anyone ever played darts? Anybody ever played darts? You know, darts. I'm not going to get the right number, but you get the idea, right? Throw a dart, and then you try to get in the bullseye sometimes, whatever way you play. Let's just play like we're trying to get it in the bullseye. What's the probability if I take somebody who's never played darts before and I let them throw darts, and I don't count it if it's out here, right? I only count the ones that happen in here. The probability that it hits the bullseye versus this triangle. Why is the probability it hits here less than the probability it hits here?
Because it's little.
The area is smaller.
Area is smaller. It's little. I like it. So it's based on the area. This is kind of neat. Is this what it is, Jeff? Are you out of focus? There you go. Something was bugging me. So the probability of something striking an area, a part of this, is related to the area of that section. Does that make sense? And here's what's beautiful. If I consider the whole thing to have an area of 100%, right? Or an area of 100, or even better, an area of 1, then the area of each subsection is equal to the probability of a dart hitting it. Does that make sense? Doesn't that jive with this has got less of a chance because it's smaller, right? The probability it hits here is higher than here because this is a bigger area. Sort of like if a meteorite strikes the earth, what's the probability it hits a person is really small because the amount of land with no people is so huge compared to the amount of land with people. Do you guys know this? Or the fact that water, they're not too concerned about satellites crashing to earth because 70% of the earth is covered by ocean. So there's a good chance that it's going to hit the ocean. And of course you're like, you better hope so. Where's that thing? All right, maybe. So this is, what the hell's this got to do with our class? Okay, that's a very good question. So tell me this, if I have a probability, let me see. I want to do, let's say there's there's just no way to do it. Let me think. All right, let's just do this. It takes Jeff takes anywhere from 1 minute to 10 minutes to find his keys in the morning, right? And it's equally likely it would take me any time between 1 and 10 minutes. So if I were to draw kind of a histogram, what would it look like if they're equally likely all the way through here?
Be flat.
It'd be flat. Exactly the way the Earth isn't. Okay, I like it. Now, how tall would this have to be? Because remember what I said, if this guy's area is 1, then the area of any part of it is equal to the probability of that part of it being hit. So if I were to say something like, what's the probability it takes me more than 4 minutes to find my keys? Can I figure it out from this picture? Yes, I can. Stay with me. Would you agree that this picture is much better in terms of areas than this picture? Yes. You don't even want to try to figure out how to find the area of this section here. So screw that picture. I have a much better picture, right? The question now is, how do I make the area 1? How do I make the area of this 1? How tall would it have to be? Well, how wide is this? How wide is this?
10.
No, it's not 10.
9.
There you go.
Tricked us.
I really didn't, but okay. So it's 9 across. I want the area to be 1. I want the total area to be 1. That would be like all the probabilities being 1. So how tall does it have to be? I want something times 9 to be 1. Something times 9 to be 1, right? So what does this have to be? What do you multiply by something to make it 1? You multiply by
0?
it. Sorry?
0? By itself.
9 times 9 is 81. 9 times 0 is 0. 9 times its...
You have to flip it.
Yes.
Or something?
Reciprocal. What is 1/9 times 9? What's 1/9 times 9? 1, yes? Little man says yes. Okay, I like it. So now watch this. Was that hard? If this was 20, what would this be? 1/20. So really, it's kind of like each piece of this has a 1/9 chance of happening because there's 9 minutes, right? There's a 1/9 chance it'll happens in the first minute and a 1/9 chance it happens in the second minute. That's why this makes sense. They're all equally likely. So what's the probability it takes me more than 4 minutes? Do you see how that question becomes, what's the area of this rectangle? So if I draw the probability distribution and I make sure the area is 1, the answer to any probability question equals the area that it defines. And yes, we are doing this at the tail end of class, and yes, we will do more of these next time, but what's the area of this? So this is equal to area. What's the area of this? How wide is it? How wide is it?
6.
6. How tall is it?
1/9.
1/9. So the area is 6/9, which is 2/3, which is 66.7% roughly. So it'll be, what's the probability it takes me more than 4 minutes to find my keys in this situation? About 66.7%. It's about 2/3 of the picture. So these are called uniform probabilities. And they are our first real example, besides normal, they're the first real example of continuous probabilities, right? Because I could say it's more than 4.2973, blah, blah, blah. It's continuous. Doesn't have any gaps. It's continuous. All right, so obviously we'll do more examples of that next time. I was trying to squeeze it in here at the end. So this is from chapter 5. Chapter 5 is about continuous distributions, and then more specifically uniform distributions, not unicorn. Binomial, real quick. Why is binomial a discrete distribution? Give me an example probability question. Wouldn't it be out of 44 people, we have 7 of them smoke, right? Could it be what's the probability that you get 7.392174 people smoke? Does that make sense? Think about it. Does me asking what's the probability you get 7.39214 people smoke? Does that make sense? Can you have 7.2934 people?
No.
No.
Thank God, no. So binomial distributions are examples of discrete probability distribution because they could only be whole numbers, right?
Is that because it could only work on the equation? Like the formula?
Sure, but it's more than that. You could try to plug in decimals into the equation, but it would just freak out. It's because I'm talking about discrete things like people or dogs or paintings or whatever. I can't have 1/4 of a dog. I hope, right? But this, I could find. I could say what's probably takes me more than 1/4 of a minute, or 7 3/4 minutes, or because I can break down time as much as I want to. This is a continuous distribution. Okay, all right. So that was a lot slammed into time. So we'll focus on uniform at the beginning of next class, and of course, we got the quiz. It's going to happen after class, and let me know if you guys want to do the study group thing. Let me know. And I got my extra office hours tomorrow, right? 11 to 12, as always, on Tuesdays. It's crazy. Okay, that's enough. Let me know if you need to hang out. Otherwise, you're free to go. Everybody's good? All right, I'm gonna head out. See you guys later.